Hi Dylan, thanks for your email. I've got the question that you're asking here. And before we start this, I want to address your other question about the different notations. So in this question, what we're doing is differentiating with respect to time, because we're talking about rates, and these are velocities, like how fast is well, I guess not just velocities, but how fast is distance changing over time? How fast is, things changing over time? So if you have functions that aren't defined according to the variable t for time, then every time you take a derivative of that variable, you need to multiply by, d times the variable over dt. So it's very much like implicit differentiation when you were doing x squared plus y squared equals 25 or something like that, and you were trying to find dy dx. Then dy dx means that we are defining the function according to x in terms of x. So whenever we're taking the derivative of an x term, we can just use the power rule. But when we're taking the derivative of something that's not defined according to x, then we need to multiply in that variable dx, like dy dx. And so that was how we handled the implicit differentiation for a variable that's not what we're trying to differentiate with respect to. Okay, I hope that makes sense. So with this problem, what I would do is I would make two diagrams, and I don't know if you're required to prove that these are similar triangles. If you are, then you've got two angles equal. You've got the 90-degree angle equal, and you've got these angles down here equal because of the elevation of the lamp post. So you have angle-angle similarity between the two triangles. So for the larger of the two triangles, we know that the lamppost height is 10, and we know that the distance from the lamppost all the way out to the edge of the shadow is x plus s. If we look at the small triangle, we know that he's 1 meter, and that we're calling this distance between him, like the length of the shadow, we're calling that s. So in similar triangles, we can set up ratios because we know that everything is just like a blown up version of the other image. And so we can say that 10 over x plus s is equal to 1 over s. And if we just cross multiply, that's probably the easiest way to simplify this. We have 10s equals x plus s. And if we solve the equation for s, we would have 9s equals x. And so that's the equation that relates s and x. And if we want to solve for ds dt, which is what it's asking for here, let me just move that up a wee bit so that we can continue on below. Then if I differentiate this equation with respect to t, then neither one of the variables is assigned according to t. And so I can take the derivative of 9s is 9, and then ds dt. And the derivative of x is just 1, and then I have to multiply by dx dt. Okay. So we're trying to solve for ds dt, so we might as well rearrange the equation as 1 over 9 dx dt. And I think in the question you're given that the person is moving 2 meters per second, and they're moving, are they moving towards the lamppost or away from the lamppost? I think. I don't think it specifies in your question. So what we do know is dx dt, because we're given that it's 2 meters per second. And so if we just solve for ds dt by substituting in the 2 meters, if he was going towards the lamppost, it would actually be minus 2 meters per second because he's closing in on it, he's reducing the distance. So it may not matter here if they weren't specific about what direction he's going. And so this is what I would get for the rate of change of ds dt, how fast it's changing, is 2 over 9 meters per second. it's funny that they say at the point where the person's 5 meters from the lamp, that actually doesn't really come into play, that information. You don't need it in the equation. So that's how I would handle this question. If he's done it differently and you want me to have a look and explain the difference, then please send me another email and send me the screenshot of his work. Maybe I'm misinterpreting what you're being required to do in that case. Okay, thanks.